to present this work, which has been done with a lot of people from ex-LSV. So Beatrice, Benedict, Patricia, and Matthias. And of course, I wanted to talk about synthesis because it was a great opportunity to use again. Okay, so this is this. Oh, now it doesn't work anymore. Je clique quoi? Sur l'écran. Ah, okay. But non, je veux pas que ça avance tout seul. Okay. Okay. So this slide. So Natalie showed us a slide that came from her PhD defense. But this one is even older because it comes from my very first talk as a PhD student. And it was actually given to me by Paul. I haven't designed this. And it's made with Gastec. And so we're going to talk about synthesis as the church presented it. So what's the synthesis problem? So you're given an open system which receives input. Oh, okay, no, sorry. Which receives input from the environment and responds with outputs to the environment. And in a synchronous way, we have a clock that synchronizes this interaction, and you're given a specification that specifies how the system should behave. And with that, you want to decide whether there exists a program for your system such that every execution of the program in parallel with the environment will satisfy your specification phi. And this, however the environment behaves. And the second part of this is if such a program exists, you want to synthesize it automatically. Okay, so this has been, the question has been asked by Church, and a few years later, Buchy and Landweber answered that it was possible, and they used an encoding into a game framework because they figured out that the environment is, is like an opponent in a two-player game. Ben, vas-y, ferme. OK. Non, mais tu vois, là, ça quitte le mode... si tu mets en plein écran. Sinon. At full screen, I have a number of the slides. Yeah. OK. OK. And a few years later, Rabin came up with another positive answer to that question using automata theoretic presentation, tree automata, sorry, because his vision of the problem was that what we want to synthesize actually is a tree where the directions of the tree are the different actions from the environment, and the way the system should answer to this is the label to the node of the tree. And even later, Pnueli and Rosner has re-examined the problem with LTL specifications. And well, all in all, it's the problem is decidable. And you've seen in the talk of Jean-François that now you have tool to answer to that problem. And Jean-François is trying to making it even easier to use that kind of tools. When I was presenting or talking informally to people about that problem, usually I said that the specification is given in a logical formalism, and people was telling me, okay, so it's satisfiability that you want to do. So I want to emphasize the difference between this problem and the satisfiability problem. So if you look a bit more into the details here, so the inputs from the environment are given by a variable, X, that ranges over a domain, finite domain, and the system will answer with the variable Y. And so what we want to synthesize is a function that, given a finite history of inputs from the system, gives you the desirable output. I don't know where the pointer is. Here, okay. To output at that moment. And so an execution of the system is a sequence of input and output, input, output at every timestamp. And each output is actually given by the function applied to the history of inputs received until now. Okay, so let's look now at a simple specification. I want that someday X is equal to 1. So this is obviously satisfiable, but it is not realizable because the variable X is not controllable by me. If I want this formula to be satisfiable, I need to output a 1 in the X variable somewhere during the execution, but it's not in my control. I want my program, my execution, to be correct. However, the environment behaves. So even if it decides not to output one at a moment. Okay, so now I'm looking at another specification. Okay, I've understood that I cannot control the input variables, but what about saying this? So I want to output in the variable y, 1, if and only if in the at the third step, the x variable is equal to 1. So this is also obviously satisfiable, but it is not realizable neither, because I want to synthesize a reactive system. And you see that the value of the variable y at the time step r depend only of what has happened in the input variable so far. So at the first time step, I have no idea of what the environment will do in the third time step. So there is no program, no function that allows to realize this formula. Okay. So now what we're going to talk about is synthesis of distributed systems. So the problem is changes a little bit, and now you're given along with your specification, you're given an architecture. So a set of processes, a finite set of processes. Here you have 4, and the way they communicate with each other. So here you see that process 1 is allowed to communicate. I really don't see the pointer. Process 1 is allowed to communicate, it's here, with process 2, but not directly with process 4. So this is the input of your problem. You've given a set of processes and the way they're allowed to communicate. And your specification constrains the behavior of the global system. And so now what you want to synthesize is a local program for each process of your system. So you don't want to synthesize like a global controller that sees everything and gives orders to everyone, but each program depends only on the local view of each process. And you want that each program, that the joint behavior of all your programs, and with the uncontrollable environment satisfies your global specification, whatever the environment does. And you also want to synthesize it if it's possible. Okay, so this is much more difficult. So let's look at this very simple architecture, more into the details. So here you have 2 processes. The first one receives an input in a variable x1. The second one receives input in a variable x2. And there is a communication between the process from the left to the process to the right through a variable y. Okay. So what I want to synthesize is a program F1. And when I say that I want that the program or strategy is local to the process, it means that this program only depends on the history on x1. The program F1 has no idea of what happens here, because there is no way to tell him. And also, he wants to output y1 and say what he wants to output on the variable I. And I also want to synthesize a function F2. And this function depends on the input on x2, because this I receive it immediately, and also on what the other process told me through the variable I. And I want to say, based on this information, what I want to output on the variable y2. Okay, so now if you look at an execution here, you have the sequences of inputs, x1 and x2 at each time step. And process 1 answers at each time step with y1 and I. And each y1 and I depends on the finite history of what happened until now only on x1. So here. And process 2 answers with y2 based on what he has received only on I and x2. Okay. And our problem is, okay, now if I'm given a specification, which is a subset of all the possible executions that can occur, can I synthesize a strategy such that, and what we say that every execution according to the strategy is given by, okay, if X is the infinite sequence of input that I received so far, now I can deduce, thanks to the strategy, what is the execution that is gonna happen, and if this execution satisfies my specification. So this problem is undecidable. And it is undecidable because of this architecture, where the 2 processes do not communicate at all. And it's known actually since Pnueli and Rosner, but they based their work on distributed multiplayer games from Peterson and Reif in '79. And even for LTL specifications, you cannot decide because of this kind of architecture where the two processes do not communicate at all. So if you add now, like I've done before, this communication between process 1 and process 2 through a variable I, what happens? Well, Finkbeiner and Cheveux said it's still undecidable. And why is that? It's because your specification talks about everything that happens in the system. And you can have a specification that says, okay, at every timestamp, I want that y is equal to 0. So your variable I is totally useless. It's as if the two processes do not communicate at all. And so you're back to the undecidable architecture of Pullier and Rössner. Okay? So if you think that writing a specification that is allowed to say, this communication link exists, but pretend that it does not, if you think that it is cheating, then you can consider that the specification is not allowed to talk about internal variables, and you consider only input-output specifications. And in that case, this architecture becomes decidable. So the key argument to obtain undecidability is what Finkbeiner and Cheveux called information fork. And okay, information fork, it's the precise notion may be changing a little bit depending on what specifications you allow, etc. But the basic idea is that if there is some information that one process knows, and so this one, and this one doesn't know, and reciprocally, so he knows more on certain aspect and he knows more on certain aspects, this is information fork and it becomes undecidable. Okay? So if you allow a link here and do not constrain it in any way, then this architecture does not have this information fork anymore because this process can transmit at every time step all what he knows to this one. And so this one is more informed than the left one. And so it's not an information fork. If you can order your processes in a way that you have the most informed one and then the less informed one, etc., then you can manage this problem. Okay, so you see that the best that process can do here on the variable y is to transmit the value of variable x1. Okay, it's useless to make complicated computation here because if you give x1 directly to the other process, it can do your complicated calculation on its own. And so the simplest and the best way, the best thing you can do is to transmit x1 directly. So now I'm going to consider this kind of architecture, meaning that if you have a communication link between two processes, it means that the value of the input here will be transmitted here, and that's it. But what about now dynamic networks? So what is a dynamic network? Instead of having a fixed communication link here, you consider that it can change during the execution. Okay, it can become even both ways or disappear completely. Oh no, okay, I'm too quick. Let's forget about disappear completely for now. It can change. Okay, so so you can look at that and the nice work done by Dietmar and his co-authors. They looked at this kind of problem in the setting of games and explained how to transform it and adapt it to the synthesis problem. And the basic idea behind that is, okay, the hierarchy of information can change during the execution, but as long as you have some hierarchy at each moment, you're fine, basically. What we've looked at is what we've called full information protocols with dynamic links. So the dynamic links is, as I've said, the thing that your communication here can change. It can be either both way or to the left or to the right. And again, I've forgotten, but I will add it, nothing at all. So you can imagine that it is kind of a fault. Like you think you can communicate, but sometimes it doesn't work, but it's not a permanent fault. The system can recover. Like Wi-Fi, like you're trying to connect to EduRoam and it works, doesn't work, and you have to reconnect all the time. Okay. And what is full information protocol? So it's a kind of protocol studied in distributed systems community where you imagine that what I've said to you is that the best way process to the left can do is to send all what he knows to process to the right. But you can imagine that you can do even better. Instead of just transmitting what you've received now, you can transmit all what you know since the beginning of the execution. So if your system is dynamic like this, maybe this is the first time you have a chance to send a message to process 2. okay? If you send only what you've received now, it's not much. But you consider that when you have a chance to communicate, you say all what you know, okay? Okay, so how does it work? We'll see. So here I'm gonna display an input word with what's coming on the left side as input, what's coming on the right side as input, and the communication link between the two that can change. So at the first time step, process to the left receives 0, process to the right receives 1. And what is gray is that the process to the left, from the left, knows. So he knows everything because he received the message that, okay, I've received 1. But on the right, process 2, he only knows that you have received 1, and he also knows the communication link. Okay, but he doesn't know if the other process has received 0 or 1. And now at the next step, communication is back. Okay, so process 1, let's call it process 1, knows everything, and he continues to know everything. And what happens to process 2? Now he knows everything too. Okay, so my gray zone has expanded. Okay, where is this? Okay, and now he also knows that at the preceding step, it was 0 that was input to the process to the left. And we continue. Now the communication link is broken. So process 1 only knows 1, and the fact that there is no communication, and process 2 only knows 0. And we continue. Here, process 1 only knows 0, and here is blind, and process 2 at this moment recovers the whole history. Okay, so I can continue like that. And so this is the view at the end of this sequence of input. This is the view of process 1 in gray, and the view of process 2 in gray too, okay? So the fact that one process knows more than the other is changing dynamically along the execution. So what I want to synthesize now is a program for process 1 that depends on the input. What is the input now? It's x1, this I will know every time. The communication link that occurs, this I will know every time too. And sometimes I will know x2, and sometimes I will only know bottom, which is the random dummy value to say I don't know what happens on the other side. And the same for f2, okay, the symmetric. Okay, so how does it apply? Now, at the first time step, I know everything. So my strategy says, okay, if you see 0, this arrow, and 1, you output 1. And the strategy f2 says, only if you see 1 and something on the left side you don't know, then you should output 1. At the next time, the strategy f1 says, okay, now you see 1 and everything, so you output 1. And here you will see that the strategy f2 do not depend on this input and another one, but this input will change too. Okay, it will be applied to a new word, and it will tell you to output 1. And so the history on which the strategy applies is changing during the execution. Okay, you've got it. Okay, and now if I call, as I did before, this is y1 at the moment 0, and this is y1 at the moment 1, etc. If I'm given w, which is the input word, which is now the input on x1, the input on x2, and the communication link at each time step, the execution that is compliant, that satisfies f, is given by this sequence, where I have at each time step x1, x2, the communication link, and what has been chosen by the different strategies. And so in our problem, in our setting, the distributed synthesis problem is expressed like this. So I'm given a specification among all the execution that talks about all the executions, and I want to decide whether I have a distributed program such that all the executions satisfy the specification. Okay? It's exactly like before, but the only thing that changed is the way I describe my strategies. Okay, so now an example. So this is my specification. I say that always, if I have a 1 on the left output, I have a 1 on the right output, and reciprocally. And also, if I have an infinite number of times 1 and 1 on both outputs, I have to have 1 and 1 on both outputs. So what do you think? So you wake up a little bit. Is it realizable or not in that setting? So I have two requirements. First, the two processes must output 1 at the same time. And the second requirement is if I have an infinite number of 1, 1 as input, I have an infinite number of 1, 1 as output. I don't choose the communication network, so it's uncontrollable. So nobody dares to tell me. So it's not realizable, okay? Because it might be that the process 2 never knows anything about the input of process 1, for instance, and so it cannot decide what's going on. So let's see that on an example. So if you have this input, then processes can say, okay, we have a first 1, 1 input, so be careful, we might have to output 1, 1 infinitely often, so let's output 1, 1 now, okay? At the second time step, you have that. So process 1 knows that we are fine, there is no 1, 1. Process 2 does not, but they can decide, let's say that, okay, now we output both 0, because maybe they have prepared in advance that the second time process 2 receives 1, we output 0, let's say something like that, okay? And we continue, we have 1, 1 every 2 time steps, okay? So we try that. This, if you continue like that, this execution, you will satisfy the specification. But if I look at this execution, it is the same for process 2. It cannot make the difference between the two because it doesn't see anything from the left side. So you will output the same thing as before. And process 1 knows that they have to output the same thing at each time step. So he's forced to output 1, 0, 1, 0. Otherwise, it doesn't satisfy the first part of the specification. And here, they will end up outputting infinitely often 1, 1, and there won't be infinitely often 1, 1 as input. So it will violate the second part of the specification. Okay, so this is not realizable. And if we change a little bit the specification, we say this now. So I have the same requirement, but I have to fulfill it only if infinitely often the communication link is to the left and infinitely often the communication link is to the right. So this becomes realizable, okay? What the strategy would be in that case? So at first, they're gonna be cautious, okay? So for now, we know that we do not know the same thing, so we will output 0 all the time. But we're confident that someday the communication link will change, otherwise we will have nothing to do. So now, no, not now. Now the communication links changes, okay? So at that point, process 1 sends all what he knows to process 2, okay? So all the history. So they both know all this history at that moment, okay? And they can decide together and they can see together that, okay, there has been this 1, 1 input at some point. So let's output 1 now, okay? And we continue. So they stay cautious until the next time the communication link changes again. And it will have a suspense. Now it happens, so they both know all what I've circled in blue, and they can both see that, okay, now there has not been any 1, 1 input, so let's output 0. And you continue like that, and this strategy will satisfy the specification, okay? So this was an example of what you can achieve or not achieve in that kind of setting. Okay, so the setting in which we are, so we're going to look at the synthesis problem parameterized by the set of communications link you're allowed to use. Okay, so the biggest set is any communication link, but you can choose to restrict to some smaller communication. And your specification, of course, will be allowed to talk about the network, because as you've seen in the preceding example, otherwise, well, it will not often be realizable what you ask, okay? Because if it doesn't depend on the network that changes all the time, then it's too weak. Okay, so the result is that you can decide this problem if and only if you forbid the no communication link. Okay? So if at any time the communication occurs either in one sense or the other, then the synthesis problem is decidable and reciprocally. So one sense comes directly from the proof of Knueli and Rössner, because if you allow the empty communication link in your network, then you can have an execution where they never communicate, and you're back to this totally disconnected architecture where the problem was undecidable. And for the other direction, well, at the end of the talk. So now we're going to see why, in that case, the synthesis problem stays decidable. So we're going to look first at a simpler setting where you only allow the double communication or communication from right to left. Okay? So there is no change in the sense of communication. It's just process 2 either is blind or he receives the information, and process 1, he always receives the information. Okay? And we will show that it stays decidable following this, pattern, this sketch of proof. We will first show that there is a winning distributed program for our problem, if and only if there is a distributed program with finite memory in some way I will explain to you later. Okay? Because what can be a bit unsettling in this problem is the fact that process 2 will receive from time to time an unbounded amount of information, actually. Okay? You don't know how many time steps we will have between two synchronizations between the two processes. So we will first show that you can reduce your search to the set of finite memory strategies. And then we will show that with this restriction, you can encode our problem in a game again, in some kind of game I will explain later, which is known to be decidable. Okay, so what will I call a finite memory strategy? So I want to have some kind of finite automaton. So let's say a parity automaton, okay? That will work on my execution here. And if you look at, this block, okay, so I have a synchronization at the first moment of the block, and I look at all this block until the next synchronization. Here, at the beginning of the block, I'm in the state of the automaton that I call state 2, okay? And I want that to be all the memory I need to solve what happens in the block I've circled in blue, okay? So I do not need to remember what happens up there. And if you look at what is output here, so I'm in the state S2, and then there is a communication synchronization between the two processes. And for instance, the view of process 2 at this moment is only, okay, I know 0 and 1, and then I only know 0. And I decide to output 0. And later on, in this block that starts here, I'm also in the state 2 of my automaton, the same state. And process 2, he sees the same thing. So I want him to output also 0. That's the kind of finite memory I look for. So I do not need to remember at this moment all what happened here. All what I need to remember is just state 2. Okay? So how do we achieve that? We're going to look at strategy trees, but some special case of strategy trees. So if you remember what I've just shown in the previous slide, you've seen that an execution in that kind of model can be sliced into blocks where the two processes synchronize, and then process 2 is blind for a certain amount of time, and then they synchronize again, okay? And between two synchronizations, the two processes have the common history they have is what happened before the synchronization. And at the next synchronization, their common history is what happened also in the in-between block. So the tree we were going to look at are very big trees. So it's infinite trees with infinite branching and infinite labeling, okay? So the directions of my trees are these blocks where I have a synchronization, and then process 2 is blind. Okay? So I have an infinite set of blocks like that. So my branching is infinite. And now, what will be the label of my nodes? It's okay. So in a label of the node, I will have two trees also. One tree which is the promise of the strategy of process 1, and the other tree will be the promise of the strategy of process 2. It means that according to the common history we have until now, and we both agree on this common history, process 1 have a tree which says, okay, if the sequence of inputs I receive from now is this is what I'm going to do. And process 2 says, if the sequence of input I have until this is that, this is what I'm going to input, with the difference that the two trees don't have the same branching between because process 1 sees everything, and process 2 is blind on the left side. So how do I deduce a strategy from this strategy tree? Okay, so at first, at this moment, it's the first synchronization that occurs. So I look at the root of the tree where nothing happened. And I look at, okay, process 1, he sees 1, 1. So he promises to output 0. So this is what he's going to output. And process 2, he promises to output 1. So this is what he's going to output. At the second time step, they see 0, 0. Okay. So we're still at the root of the tree. And in the tree of process 1, I say, okay, at 1, 1, 0, 0, this is what I'm going to output, 0. And process 2, I've seen 1, 1, and then I've seen 0 and something, and I'm going to output 0. And then there is a synchronization. Okay, so they both know all the history at the moment. And then I will take this direction and change the node. And I will see that process 1, he will output, okay, now we've seen 1, 1. He will output 1. And process 2, he will output 0. And at this moment, process 2 doesn't know what happens here, but he says, if I see a 0 on my side, I put 0. Okay? So from this infinite strategy tree, I can deduce a strategy that tells at each moment what I'm going to output. So there is this correspondence between the strategy we're used to have and this big strategy tree. We're interested to have strategy trees because then we have tree automata. Okay? And we will build a tree automaton that will accept the strategy trees that satisfy the specification. So I'll start from the automaton, the word automaton of the specification. I have a linear time specification, like a normal regular specification. So I know I have a deterministic parity automaton for this specification. And for an execution, I have a sequence of states that are visited. And each state is associated with a priority. And now I'm gonna build a tree automaton on this big tree. So it's an automaton with an infinite set of transitions, but a finite set of states. The set of states of the automaton are the states of my word automaton and a priority. And how will it work? When I'm in a state, and I see the labeling of my strategy from now, I look at the word automaton, okay? And I say, okay, if I want to go there, I will take the direction D, so a finite word of the execution. What will do the word automaton of my specification? He will go in the state S2, okay? So I will go in the state S2. And how do I know what the exact execution is based only on the input? It's because I have the labeling here that tells me what's going to happen. And the priority I keep here is not necessarily the priority associated with the state S2, because we're looking to minimal priority automaton. I'm keeping the minimal priority that I have encountered in this path. Okay, and I do this on this state 2. Okay, so I have a tree automaton that simulates the execution of the word automaton on my strategy tree. And we know that if this tree automaton accepts at least one tree, he will have a rational accepting run. Okay, so a rational accepting run well, I mean that if at two, so a run tree, a run of my automaton is a tree where the nodes are labeled by the states of my automaton, and a run is rational if at two nodes I have the same labeling of the states, then the sums of these nodes will have the same labeling of the states too. Okay, so we know that if we have an accepting run of these three automaton, I will have a rational accepting run. And this comes from determinacy of parity games. Okay, so now if I know that I have a rational accepting run, I know that I have a strategy tree that is accepted by this rational accepting run, where if I have the same labeling of the states of the automaton, I have the same labeling of the state of my tree. Because if my automaton behaves the same way, then it's okay if my tree is labeled the same way. Okay. Okay, so this gives me my finite memory strategy. Because, so if I look at this strategy tree that comes from my rational accepting run, I see that after the direction 0, 0, 0, 1, what I output depends on S2, K1, because it depends on lambda 1, D, lambda 2, D. And if in another branch of the tree, much longer, say, which is sigma, I'm also labeled by lambda 1, D, lambda 2, D. Okay, so this is here. Here I'm also in the same state. And so what I'm gonna output here also depends on the same strategy tree. So I have obtained that finite memory strategy that I was looking for, where I can forget what happened before the last synchronization and rely only on the current state of the tree automaton. Okay, so now that I have this finite memory strategy, we can show how we can encode it into a game. Okay, so the game we're looking at are two multiplayer games. So I have two players against an environment. So it's played on a graph. I start from a state S, and then the environment will play. It will play an action that comes from a finite alphabet. Okay, now it's the turn to the players. So player one has only partial observation of the arena. Okay, so he sees something that comes from the state of the automaton and the action of the environment. And based on this partial observation, he will decide an action. And player two also has a partial view of what has happened so far. And it will decide an action based on this partial view. Okay, and this state, environment action, and actions of the two players gives us the next state of the game. The game is played like this. I'm in a state, the environment does something, and the two players act according to their partial observations. So these kind of games are undecidable. It also comes from the work of Peterson and Reif. But we know that if player one has full observation, so here its observation is exactly the state and the environment action, that it becomes decidable. So our game will be a 2-1 player game where player one has full information, because the states of my game, the state of my arena, will be the states of this automaton that gives me my finite memory. So I start from a state of the automaton. The environment plays the input and chooses the network. Player one sees everything because he has full vision of the system. Will decide what to do at that moment. And player two, in that case, he has no complete information because the link is broken on his side. So his observation is only one, and I don't know what the other has received. And he will play based on this action. And this will give us the next state of the automaton with the minimal priority that we have encountered. And if now I have a synchronization that occurs, the next action played by the environment is now the link is repaired, then player one still has full information, and player two recovers full information. And recovering full information, and this is where it is crucial to have that finite memory property, is only the current state of the graph. Suddenly you see the current state of the graph, and it is enough to win because the current state of the graph encodes all the memory that I need to continue, as we have shown with this big tree automaton construction. So this kind of game is decidable since thanks to Van der Meyden and Wilke result. Okay, so now we have only solved the case where there is communication link in one direction. And it's basically hierarchical information, okay? We have process 1 is always fully informed, and process 2 is less informed than process 1. Sometimes he is as informed as process 1, and sometimes he is less informed. So it's still hierarchical information. And when we add the link in the other side, then the hierarchy is changing. And we can solve this by reducing the problem to the case where the communication link is always in the same sense. Process 1 will always simulate the most informed process. Sometimes it's process 1, sometimes it's process 2, but we will reduce it to the case where it will only be process 1 that will simulate the most informed process. So for an execution, an input like this, here process 1 is the most informed. So my new input will be the same. Process 1 is the most informed. And now with this input, it's process 2 that is the most informed process. And I want that process 1 stay the most informed process. At this moment, they both know this input, x0 and x prime 0, okay? So I will add a dummy synchronization so that in that execution too, both process knows x0 and x prime 0. And then I will say, okay, now process 1, pretend you're process 2 and reciprocally. So I reverse the input here. And so the view that process 1 has in the real system is mimicked here by process 2. And we can show that we can transform any input like this into an input where it's always process 1 that is the most informed. So you can write, okay, can rewrite all the histories and use a transducer to transform the inputs, the real inputs, into new inputs where you have dummy synchronizations from time to time that allow process 1 to always be the most informed of the processes. Then you also rewrite specifications so that when the process 1 is indeed playing the role of process 2, he outputs what process 2 is supposed to output, otherwise it won't work. And you can show that you can reduce the biggest problem to the smallest problem we've just solved. Okay? Okay. This is my last slide. So we've removed the case where the two processes do not communicate, because we showed that in that case, we're back to the Pnueli-Rosner architecture, and it's undecidable. But it's a very strong requirement, because when you want to simulate, to model systems where communication is unstable, it can happen that the communication is totally broken. So but what we can show is that if you have a bound, you know that, okay, communication can be broken, but only for at most case steps. It won't last longer than that. Then you can recover also decidability. If the communication link is broken and you can upper bound the number of steps where it will be broken, then it works too, okay? Because you can still reduce the problem to the simplest problem of the beginning. Okay, just perspective of this work. So the weaknesses are 2 processes and no delay. If you want to extend that to n processes, then okay. So this is a sequence of communication links with 4 processes. So at first they communicate in that direction, then the links all change, and you can have more complex communication types. Okay, so the view of a process in such a system is given by, okay, the preceding nodes in this kind of graph. Okay, so we will have to design a strategy that is based on this kind of view. Okay, and if you want to extend these results to n processes, then it might be reasonable to assume that the communication is not instantaneous, as we have said, as we have assumed here, and that the processes will receive the input of the neighbors with 1 step of delay, or maybe a k step of delays. Okay, so our conjecture is that if at each moment of the execution you have no information fork, and that would mean that there is a communication path between every 2 processes, either in a way or in the other way. So if at every time step there is this communication path, then you will probably stay decidable. Okay. What is more challenging is to assume that, because here the processes know the communication link at every moment. Okay, and that's really useful to solve the problem. So if they never know the other side of the arrow, if they never know if their message has been received or not, then the problem will become undecidable. But if you assume that they will know if their message has been received or not at the moment that the other process communicates again with them, then you do not have a bound like with the delay on the moment they will receive the acknowledgement. And then we don't know what will happen. So they will have a knowledge of the architecture, which is more chaotic. They don't know when they will learn what's happening in the architecture. And then that's even more challenging than solving the N processes and delay setting. So thank you for your attention.
Long live India and France friendship.